Hi everyone, so we're talking about optimization, and optimization is just an application of finding extrema, so finding absolute minimum and maximum values is what we're going to be doing, except this time with word problems. Okay, so in my first example, I have a particle that's moving, and it wants me to find the minimum velocity and then the time at which it occurs. Okay, so first thing I got to do is find my velocity because that's what we're trying to minimize. So generally you have one equation that you're trying to optimize, and in this case that's my velocity, so I'm going to solve for v by taking the derivative. Right, so I got my derivative, and now because I'm trying to optimize this, I need to find my critical numbers. So v is like my original equation, so I need to take the derivative. Okay, so I get 6t minus 10. That's going to be equal to 0, so t is going to be 5/3. So this is my critical number. At this point, I can do a candidates test. So that's what this says here. It's my first method. So I have t, and then I'm plugging into my original equation. I'm going to plug in my endpoints, and then my critical number. So my endpoints were given to me in the problem. All right, and if you plug these in, you should get 12, 3.666, and then 20. And I want the minimum value, which is right here. So I could say the minimum velocity is 3.666. They didn't give me any units, so I don't have to give any. And then it occurs at t equals 5/3. Okay, so that's my first method, is by doing a candidates test. And in general, this is going to be the way you want to go about doing optimization problems. However, I will show you one other way of doing it. So in this particular problem, we could have also done the first derivative test. And it's a little faster that way, so we'll run through it. So same deal. I'm trying to optimize my velocity. So I still need my velocity equation. Oops. And I still need to find my critical numbers, so I take the derivative, set that equal to 0, I find that 5/3 is my critical number. At this point, if I do the first derivative test, okay, we'll find that I go negative and then positive. The reason why I'm able to do this is because I know that 5/3 is going to be the only minimum that, on this interval. Hey, I only have one minimum, it's 5/3. I know that it's decreasing at first and then increasing, and so my endpoints cannot be smaller than 5/3, or rather whatever the y value is at 5/3. And so this method was way faster. It got me the exact same answer. Okay, I'd still take this, plug it into my original equation. I got the answer way faster. I didn't have to calculate as many values, but the bad side to it is that because I'm not plugging in my endpoints, I may or may not be sure about what the actual answer is. So in general, I would recommend you do the candidates test, but this will work sometimes. Okay, but kind of whether or not to do it is kind of up to you. You can experiment with it. Hypothetically, if I wanted to find a maximum, then this second method definitely would not work because there is no maximum on this interval. Okay, the reason why this worked is because I knew there was only one minimum on this interval, and I just needed to find it. Okay, so like this is saying, if the absolute max or min occurs at an endpoint, you have to do the candidates test. So in general, the candidates test is going to be a better way to do these problems. All right, let's do an actual word problem now. So the gist is I have a swimmer, he's chilling right here. He's right here. And he wants to go to this town. All right, he's 3 miles away, and he's 2 miles out from the shore. And so he can swim at a rate of 2 and walk at a rate of 4. And so it's wondering at what point should he swim along the shoreline so that the time it takes him to get to town is a minimum. All right, so we kind of have to balance him swimming versus walking. Okay, so what I'm going to do is label some stuff. I'm going to label this distance right here x. So this distance right here, I'm going to label this as x. And the reason why I'm labeling this as x is because this is the distance along the shoreline that he's swimming. And that's what the question's asking me. So I'm going to label this x. Now, if this whole distance here is 3, then that means that the distance between wherever I land and the town is going to be 3 minus x. Okay, I also need to find the distance in which he's actually swimming, because he's out here. He's actually going to be swimming this distance. I can use the Pythagorean theorem for that. So I'll get x squared plus 4 inside of a square root. Okay, at this point, I have to come up with an equation that I know in my own brain. Okay, similar to related rates. And I know that distance is rate times time. Okay, it's asking me to minimize my time. So I know that time is distance divided by rate. All right, so let's come up with the equation that I'm trying to optimize. Okay, I'm trying to get a minimum amount of time. So I'm going to set it t for time. Okay, so the time he's going to take is distance divided by rate. So the distance that he's actually swimming is the square root of x squared plus 4. The rate at which he's swimming is 2 miles an hour. Okay, so that's the time it's going to take him to swim. Now the distance that he's going to be walking is 3 minus x. The rate at which he's walking is 4. All right, so this is the time he's swimming. This is the time that he's walking. Okay, so this is my equation I'm trying to optimize. At this point, we take the derivative. Derivative's a little messy, so we'll get x over 2 times x squared plus 4 to the 1/2 minus 1/4. I did a little simplification. Okay, and at this point, we need to plug this into set this equal to 0, solve for our critical numbers. And I used my calculator for this. I ended up getting x to be 1.1547. And it looks like we're in hours. Wrong. We're not in hours, we're in miles. Okay. So what we found is that if he swims 1.1547 miles along the coast here, now that's not this distance. We could calculate that distance, but that's not this distance. It's this distance right here. Okay, if he travels a little over a mile along the coast here, swimming, and then he walks the rest of the way, then that will be a minimum. So he'll get there in the shortest amount of time. All right, let's do another one. This next one is cost, and it's very common. Okay, I know that you have another problem on your notes, but we'll be doing that as a warm-up. Okay, so here it's asking me to find the dimensions of a 12-ounce can that can be constructed with the least amount of metal. Okay, so basically what we're doing is we're like comparing volume to surface area, or we're going to use volume to help us find the minimum of surface area. Okay, so first I got to figure out what am I trying to optimize. Well, I'm trying to optimize my surface area. I'm trying to find a minimum surface area. Okay, and that equation is right here. They gave me my volume. Okay, so first of all, let's set up some of my equations. I know my surface area is 2 pi RH plus 2 pi R squared. Okay, now, so this is what we're trying to optimize. Normally, the next step would be to take the derivative. However, taking the derivative was going to be kind of tricky because I have two variables here. So if you have two variables in your equation you're trying to optimize, you're going to need to make a substitution, like what we did earlier. That's why they gave us this stuff about volume. Okay, so I know that my volume is 12 ounces, which is about, they said, 355 centimeters cubed. Okay, this is my volume. Now, if I take this and I solve for H, now I know what H is with respect to R. So now I can go back into my surface area equation and substitute H out, just like what we did with related rates. Hey, we do not want two variables in my surface area equation. Whatever I'm trying to optimize, I don't want two variables, I only want one. So I need to take other information they give me and make a substitution. So now I have this in terms of just R. So I have 2 pi R squared plus 2 pi R times 355 over pi R squared. All right, so we do a little bit of canceling here. These will cancel. So I end up with 2 pi R squared plus 710 r. Okay, so this is my surface area equation, and it's much better than it was before because now I don't have an h in there. I only have r. So at this point, I'm going to take the derivative. All right, so I get 4 pi r minus 710 over r squared. Okay, I'm going to set this equal to 0 and solve for r. Okay, and whatever I find for r here is going to be my minimum. So again, I use my calculator, and I end up getting that r equals 3.837 truncated to 4. Okay, and we're in centimeters. Okay, so I found my minimum radius. Now, using this, I can find h, so I'm just going to plug back into here. And I get that h is 7.674. And I'm still in centimeters. Okay, so a lot of the time, when you get to this point, you're only going to have one answer. In this case, one answer for r, and I know that this is a minimum because it's the only critical number that I had. And it has to be a minimum because that's what I'm trying to find. Other ways you can verify is by looking at a graph in your calculator just to make sure. But in general, this should work. Or alternatively, you can use the candidates test, make a sign chart, and make sure that you're good. With problems like this, it's a little bit trickier because you don't have endpoints to test. And so you kind of know that the only critical numbers that you get are what you're looking for in the problem. Otherwise, the problem would be different, pretty much. All right, so that's it. We're going to do the other problem you have on your notes as the warm-up tomorrow. So I'll see you all later.